welcome everybody. It's my pleasure to introduce Dr. Gilles Ferrand. Gilles is a research scientist at Riken, the Astrophysical Big Bang Laboratory in Japan. And he did his PhD at the Institut de Recherche en Astrophysique et Planétologie at the Université de Toulouse. And then he did his postdoctoral work at the University of Manitoba, where he was a CITA National Fellow from 2011 to 2013. And today he's going to be telling us about supernova and supernova remnants.
Thank you, Jennifer. So I'm glad to be back. So yes, I was affiliated with CITA some years ago. Now I'm visiting the Dunlap, and I want to tell you about what I'm doing and what we're doing in our group about linking the supernova and the supernova remnants. So first I'll start with some general introduction on supernova remnants, and then I will present what I've been doing so far, so 3D simulations of the evolution of a supernova remnant, a young remnant, starting from initial conditions, but like by hand. And then I will introduce very generally what people are doing for simulating the supernova itself, and so how we want to use it as inputs for the supernova remnant phase simulation. So supernova remnants, so the year is 1572, and people are looking up in the sky. There's a new star in the sky, which is reported by Tycho Brahe. This is this nova stella on this plot, and it stays for like a few weeks, and it vanishes. And when we look at this location 500 years after, with X-ray telescopes, we see this, which is so the remnants of an exploded star. So this was not a new star, but this was actually the death of a star. This was a supernova, and this is the supernova remnant.
Where did you find the etching of the people discovering it?
I think it's, yes, it's in l'Astronomie populaire, a popularization book from Camille Flammarion from the late 19th century. So it's not from that time, okay? This was not made at the time of the observation, but that was made in the late 19th century as for storytelling. This is authentic. I mean, this is from Tycho Brahe. And so I think supernova remnants are really important. There's a key link between the stars, the life cycle of stars, and the galaxy, the ambient medium in the galaxy. So what you see here, these are hot metal-rich ejecta. They are expanding in the ISM. They are going to eventually deliver all the elements that were forged inside the star and at the time of the explosion itself, so in the ISM. So you know that stars can produce elements up to iron, which is the most stable, and then all of the rest must be produced by some explosive nuclear synthesis process, and people have been thinking about supernovae. Actually, it's not that obvious that supernovae can produce them all, and so people are exploring other possibilities. But so certainly they are a key player in the enrichment of the galactic medium. And this ball of ejecta is expanding super fast. They are vastly supersonic, so it's driving a powerful blast wave which is eating the medium, which is so injecting inert energy in the interstellar medium and turbulence, including magnetic field turbulence. And this blast wave, we believe, I mean, we know that it can accelerate charged particles, and so we believe these are the main sources of cosmic rays, at least in the galaxy. So I was working, the focus of my work before was more on particle acceleration, and just quickly to recall the observables of cosmic rays. So this is the all particle spectrum as observed on the Earth, which is an amazing power laws, or many orders of magnitudes. And at the highest energies there, more radius in the galactic field is more like the galaxy, larger than the galaxy itself. So these ones are probably extragalactic. But up to probably at least the knee, maybe more, we are looking for sources in the galaxy. And so from the energy budget and other things, we think that supernova remnants are good candidates. And as I said, we know a mechanism that produces power law spectra like this as observed at a shock wave. Now to see particles being accelerated, it's difficult because these are charged particles, so they're deflected by magnetic fields. So you cannot really do cosmic ray astronomy. So I cannot really show you a map of where they're coming from. They're coming from everywhere. So this is just some measurement of the anisotropy, and it means basically that it's isotropic up to at least this region. Before I had a plot showing Auger results suggesting that there was maybe a source at the very highest energies, but even that fell down. But still, if we cannot trace individual cosmic rays to the sources, we can see them when they are produced in the sources. So let's have a closer look at the emission of a remnant. So this was a color composite. So let's explode it. This is a different remnant, actually. This is SN 1006, which was observed. So in year 1006, we have Chinese records and others. And so I think this one, Jennifer likes this remnant, right? So you have maybe a conflictual relationship with it. But this one has more bilateral shape, and so the exploded stars, the hot ejecta, they are shining in X-rays because they are very hot. Sometimes you see also the blast wave traced in optical. And the energetic particles, you see them at both ends of the spectrum. The energetic electrons, you see them shine in radio up to X-rays, and you don't really see them in between. So that's synchrotron radiation from energetic electrons, and they also radiate in gamma rays via inverse Compton mechanism. And also in gamma rays, you have energetic protons via pion decay, so collision with ambient protons that produces gamma rays. And so we know that there are energetic electrons in supernova remnants. This is very common to see them in a radio synchrotron. And recently we've been able to observe them at TeV energies, but it's proven difficult to disentangle radiation from electrons and protons. The ones that shine easily are the electrons, but they're like 1% of cosmic rays, so really we're after the protons. Okay, so I'll come back a bit to this. So this is a snapshot, so 1,000 years, after the explosion. And of course it evolves over time. They live for tens of thousands or hundreds of thousands of years. It's the youngest one we know in the galaxy. This is Tycho at maybe 500 years. And so with the Tycho SN 1006, we're talking about young remnants which are still ejecta dominated, so the dynamics is still dictated by the initial explosion and the motion of the ejecta. And eventually they will enter some self-similar phase, which is known as the Sedov-Taylor phase, before radiative losses become important. And then they will enter different phases, and eventually they will merge into the ISM. But so I'm not concerned here with the late phases, but more with the young phases, both for particle acceleration, which I was doing before, and not to link them with the explosion, which is like the initial condition. So the question will be, for how long can you see the impact of the explosion? So it's been, okay. So this is just a few of them. We know many more, and So I don't have time to go in details maybe, but I wanted to briefly introduce the catalog that I did and that we put online with Samar Safir at the University of Manitoba. So there's already a list of remnants as seen in the radio. But our focus was more on high energies, so X-rays and gamma rays, and here things were scattered, and so the point was to provide a unified way of all SNRs, including candidates and recent observations, and something that's up to date, like in the X-ray, gamma ray domains, you get pretty much weekly updates. And so this is something that you can, how do I get, I guess I have to choose. So you can find it. No, this is, you can find it at this address, and first you get the list of all of them, so that's 381 remnants or candidates that we know in the galaxy. And the first column is giving you, those columns are some properties of the remnant, and the second part are high energy observations. So whenever you see the name of an instrument, it means there's a record. If it's black, it means that it was actually not seen. And if it's colored, it means that it was detected or that it's extended. And so if you click on a record, like I don't know who this one is, you'll get a more detailed list with all the observations at high energies and what people think they have observed. Like, is it the P-win, which is not relevant for me, or is it the shell that they're seeing, or both, or things like that with links to references. Okay. And if you have corrections or comments, you will find a link to send us a message. Samar and I, and okay. What is that? Why did you do that? Okay. Yeah, so these are some statistics. You can find them on the web page. So a few hundreds of them, and we are working with Samar on improving the interface and adding maybe a map and adding images also. So Jennifer had been collecting radio images, and with other people in the group at the U of M, we've been collecting also X-ray images. And this is not all of them, but a fair sample of them. Jennifer did this montage some time ago. And so this will soon be available. And so you see that they are not like equal. Some are nicely shaped and very well observed by all instruments, and others probably were not detected this wavelength. But so I think that for supernova remnant studies in general, like be it to check if there are sources of cosmic rays, or what I'm going to talk next about, things the impact of the progenitor or the explosion mechanism, you should probably get two kind of like orthogonal approaches, like doing some simple modeling on as many remnants as you can, do something statistical. So that's the kind of thing you have been doing, Jennifer, with bilateral remnants to see how they correlate with, how their shape correlates with the galactic magnetic fields on average, even though for a single specific one you may not be conclusive. And then for the ones that are really well observed, we can do a more detailed modeling. And so now I'm going to show you how we can do this. I've been doing simulations of the evolution of a remnant in 3D. And so up to now, I've been starting at some small edge, but not from the explosion itself. Okay, like So this is a case that was like a Tycho-like remnant, and I was starting at 10 years, I think, and doing hydro simulations with the code Ramses, which you may have heard about this code, but it's been used for cosmology mostly. It's reused here for Supernova Remnants. And that's a project that started when I was at CITA exactly with Anne de Courchel, and the point was to see the effect of particle acceleration at the blast wave. And so to do this, I coupled Ramses with a model of particle acceleration. So before that, during my PhD, I was actually simulating the time-dependent building of the spectrum of accelerated particles. But in 3D, that would be too expensive. So here I'm instead using a semi-analytical model of acceleration, including the back reaction of particles on the flow, which comes from blazing. And so this model is able to predict from shock diagnostics to predict what particles you get accelerated at the blast wave, and most importantly, how that would affect the blast wave in return, because if SNRs are efficient accelerators as we believe, then it has to influence the energy budget of the SNR, and it has to affect the SNR itself, and so it should be visible. And so indeed, this is what you get. This is a slice of the density. So I'm using a slice so that you can see the structure. And so this is just the shocked region. So this is the blast wave, which is expanding in the ISM. So the purple stuff is shocked ambient matter. And inside, all of it are the expanding ejecta. This part is still freely expanding, and this green part is shocked ejecta. So this is called the reverse shock. This is a shock that's going back inside the ejecta as they're being decelerated. So there's always these two shocks, actually. The blast wave, there's a forward shock, but there's also a reverse shock going back inside. And so this interface between the ejecta and the interstellar medium, this is called the contact discontinuity. This is unstable in 3D. So this is a Rayleigh Taylor instability. Okay, and this is why you get the fluffy aspect that you've seen in the observations. And so this is the reference case without particle back acceleration and back reaction. At the bottom is the same, but I put particle acceleration at the forward shock, and I take into account the back reaction of the particles on the shock dynamics, and you get a shock structure that is more compact, so not as extended and denser here. And this actually matches better observations of something like Tycho.
Closer to 7?
So it's, yeah, something like that, yeah. So, because the reference case was a very strong shock, gives you a ratio of 4. And so it's a bit more in that case, yeah.
Is there anything else that's going on between the top and the bottom about the effect of the particles on the... What else are the differences between them?
Oh, on this plot, yeah, that's what you see, essentially the difference in compressibility, which makes it so more dense and a bit more compact. And so from observations like Tycho, when people try to get the ratio of like these waves, they obtain something that's too compact compared to what would be expected from like pure adiabatic hydro. And so this is an indication that actually some energy is missing, and so there's a straightforward way of explaining this. It's add particle acceleration at the shock. But yeah, and so just a word on the co-moving grid. So this is a time evolution. It's from here. So really what is happening in real life, on the left, something expanding, but what I simulate is on the right. So I'm working in a co-moving grid, just like cosmologists do. So like the global expansion of the remnant is factored out. And so I do that by doing some transformation, changing not only not just the coordinates, space and time, but all the quantities are rescaled by a time dependent factor. And so when you do this, the Euler equations, they are unchanged if you have a self-similar expansion. If you have a different expansion law, you get an extra force that you have to add. So because you are in a non-inertial frame, so you have some inertial force that you have to add to the equations. But it happens there is already an inertial force inside the Ramses code. It's called gravity. So that's the way I'm doing this. I'm just replacing gravity by the acceleration that's needed to compensate for the expansion. There's other ways to do this, but I tend to think they are more complicated. I think that's a very straightforward way of doing this. Oops. Yeah, maybe show it again, and so you see all the related or fingers are growing initially. And yeah, again, the left is a slice. This is a projection of the density squared, which is a proxy for the emission. But really, this is just hydro. So to get to the emission, to be able to compare with what I showed you at the beginning, you need to compute the emission from the remnant. And so two things. There's the thermal emission from the plasma itself, from the ejector, which depends on the temperature of the ionization state. And there's also the non-thermal emission from the accelerated particles. So the thermal emission is X-ray energies, and the non-thermal emission is broadband from radio to gamma ray. So this work that I did when I was at the University of Manitoba with Samar Safiarb. And so briefly, to compute the thermal emission, you need the plasma density. Okay, you need the electron temperature. Actually, from the hydro, you get the proton or ions temperature. So you need, and it's not clear how actually electrons are heated at the blast wave. They're probably not heated immediately as protons, and you need some recipe for the heating of electrons at the blast wave and the way they equilibrate with the protons downstream. And you need the ionization state of the plasma. And now, a complication here is that for young remnants, they are out of equilibrium. So the way it works, so there's collisions between energetic electrons and ions, and eventually all the species will reach some equilibrium state. But these remnants, they are too young to reach collisional equilibrium. So you have to actually make the time-dependent computation. Right, so people have been doing this in 1D, like people like Herman Lee or Pat Node and Slane. But again, in 3D, that would be really too much. So what we do is we post-process this. So we just record some quantities like the ionization timescale, which is the sum of any dt, so that after the hydro simulation, we can compute the emission. So with all that, we use an emission code to compute the thermal emissions. There's a continuum emission, there's lines from elements, some are labeled here. And so this is an integrated spectrum where you see the difference between, so off means without particle backreaction and on with particle backreaction, and you see the impact that it has. It's more visible, so black is all of the remnant, red is the interior, the ejecta, and blue is the outer shell of shocked ISM. And you have the most impact on the shocked ISM because I'm doing acceleration at the forward shock. And the main effect is to reduce the temperature of the plasma so that the emission of the plasma goes down. Like it's expected. Like you put more energy into particles, and so you get less energy into your plasma. And so that's that's integrated, but again, these are 3D simulations, so you can produce maps by projecting the cube. You can produce maps of the remnant, and you can produce maps in selected bands that correspond to different elements, and so you can see how it varies with or without acceleration. And again, because we have the full 3D cube, we have all the information, so we can do more. We can do things like get the velocity profile along some line of sight. So this is something that was done for the preparation of the Athena mission. So I just gave some of my data to Randall Smith, who did some simulations. So for some silicon line, assuming we could blend from the observations the different shifted lines, the question was, are we able to reconstruct the distribution of velocities from a feature in the remnant? And so the answer was like, so for with something like XMM, which is flying now, it has a sensitivity but not the energy resolution to see that. So what was called at the time AstroEdge has the resolution, but the sensitivity is not as good. And the proposed Athena would get both the sensitivity and the resolution, so that you would be able to probe the velocity distribution deep inside the ejecta, which is important to put diagnostics on the explosion itself, which is going to be the main topic of the second part of this. And so yeah, but so Athena, so that's a mission it's proposed, and but not before at least 10 years. So the AstroEdge was actually launched and named Hitomi, and lost very soon after because of a string of human errors. And there is going to be most likely a recovery mission. And so with my new boss, we were thinking about if we can, what could be done for Hitomi that would really make use of the 3D information that we have for the X-ray mission. Oh. So yeah, this is X-rays, and at the highest energies. So it's been just like 10 years maybe that we can really do gamma ray astronomy and image supernova remnant shells with instruments like S, and we are just starting to build the next generation instrument, which will be the first observatory of like not just an experiment, but an observatory open to the community for gamma rays. So the Cherenkov telescope arrays 2 sites in the north and in the south. And so this is for particles, but so to compute the emission from the particles, you need more. So the acceleration model is giving you what's happening at the shock front. So you have to transport the particles in the shocked region, accounting for losses, adiabatic losses for both electrons and protons, and also radiative losses for electrons are important. And to compute the emission, so pion decay, it's collision, so protons, so you just need the density. Compton emission, inverse Compton, you just need some ambient photon field. For the synchrotron emission, you need the magnetic field. And so here, you will need to define what the magnetic field is. And here you get another back reaction loop, in the sense that accelerated particles are known to be able to generate themselves magnetic field turbulence and enhance the magnetic field. So I won't get into details here, because particle acceleration is not the subject of the talk today. But this is an example of a non-thermal broadband spectrum. So string synchrotron emission from electrons in red from radio to X-rays, inverse Compton from electrons, gamma rays in green, and pion decay for protons, gamma rays in blue. And the thin one is without magnetic field amplification, and the thick lines are with efficient magnetic amplification by the particles at the shock front. And there's a lot of evidence, like both theoretical and from observations, that the magnetic field at the blast wave of young remnants is much higher than it is on average in the galaxy. And it's probably caused by the particles themselves, by the streaming ions ahead of the shock front. And this affects their emission. So you have to do this all together. And so in particular, it affects a lot the emission of the electrons. So it's not so obvious on this one, but it makes the emission from electrons more concentrated really at the blast wave. It doesn't affect so much of protons. But I mean, anyway, at very high energies, you cannot really get images at this level of detail, so it's more about the spectrum maybe. And what it does, magnetic field amplification in general, that it will boost the cutoff of protons and it will kill electrons. And it's important that instruments like CITA are able to push to the highest energies. And so just...
There a reason that you're not putting French in the camera?
So, yeah, well, usually it's subdominant in this, yeah. So sometimes, yeah, people do it, but it's, I mean, may depend on specific cases, of course. But in general, these are the three most important ones for this, for typical SNR conditions. And so, yeah, this is just like putting things together in X-rays, but both thermal and non-thermal. So you get the simulations on the left, and this is again observations of Tycho on the right. And again on the top, this is without particle acceleration, and at the bottom with. And so the greenish part is thermal emission from the ejecta. And the bluish part is non-thermal emission from the electrons. And you get, because of magnetic field amplification, you get a thin rim, more like in the observations. And also you get, as I said before, a more compact structure. And so the takeaway message for particle acceleration is that even if it's difficult to see energetic protons, because it's difficult to tell at the highest energies if it's hadronic or leptonic, if they are accelerated efficiently, they do impact the dynamics of the shock wave, and so they do impact the thermal emission of the plasma that we do see, and so we get diagnostics from this thermal emission, and they do impact the evolution of the magnetic field that they can amplify, and so they impact the emission from electrons, synchrotrons, that we do see also, and so we also get diagnostics from this. So even if we don't always see the protons, we have plenty of ways to infer that they are actually there, the energetic protons. Okay, but so that's sort of a review of what I've been doing so far. And this was kind of my perspective slides before, at least when I was visiting CITA before. So now I have some updates on this, because really here I was starting from a clean initial conditions for my remnant and really focusing on the evolution of the blast wave and things that are happening at the blast wave, like so ionization, particle acceleration at the blast wave, from fairly simple initial conditions and in a uniform medium. But things are more complicated, and actually you will have to take into account where it's coming from, the explosion, the kind of progenitor, and where it is, in what environment it is expanding, which is unlikely to be uniform or steady. So for the impact of the environment, so we had some other people at Saclay would started to work on this. People who work on the ISM and they are interested on the feedback of supernovae. And we are working on supernova remnants, and we are interested in how it evolves inside a more realistic ISM. So we had started to look into this. But so my focus today will be more on the source, where it's coming from, the explosion and the progenitor. And so here it's useful to recall the distinction between the different kind of supernovae. So yeah, does it look complicated? So this is actually a simplified version, right? That's like the main ones, okay? So the classification of supernova, you know, is from observations. And so historically it was like, do we see hydrogen, and then do we see silicon and helium and so on. And so you get this classification, and then afterwards, people realize that most probably this type called 1A was different kind, and is believed to be the thermonuclear explosion of a white dwarf, when all of the others, so the type 2 and also 1B, 1C, are believed to be the gravitational collapse of a massive star, with variations which, for the most part, are explained by what envelope there is left around the massive star when it collapses. Like, does it have a lot of hydrogen or not, or helium and so on, which depends on the history of stellar winds, essentially. So that's kind of be explained by difference in winds. But so again, there are more cases. There are more exotic cases, like, you know, like as observations get more numerous and more precise, observers find something that's atypical, and then it becomes one new class, which is made by just this supernova. And so, and there's also the super luminous supernovae, which are probably from other mechanisms, different kind of engines. So I'm not going to get into that, but let's just contrast the thermonuclear one, so type 1A, so Tycho is known to be type 1A. And the core collapse one, this is Cassiopeia, which is A, which is probably a type 2B. A fairly young one also, maybe like 300 years. But we have no convincing historical records for this one, no sighting. And you see that the morphology immediately seems to be more complex. And actually, it's been argued that, in general, the remnants of core collapse supernovae have a more complicated geometry, more asymmetries than the remnants of thermonuclear supernovae. You can check Lopez's work in particular. So with my modeling so far, the way you deal with this is by setting different initial profiles. That's a thermonuclear case, what you've seen before. These are like just radial profiles of density in red, velocity in green, and pressure in blue. So this jumps. This is the radius, so this is the forward shock. This is the reverse shock, and the shocked region. And so for a core collapse one, a thermonuclear one, it's typically 1.4 solar masses. It will be a few solar masses. For core collapse, this is for more massive stars. And usually people will use a steeper power law for the. So in general, like the ejector profile is modeled often by a power law, R to the minus something, and it's taken to be steeper for the core collapse case. And one major difference is that massive stars will have winds, and so it will not explode in a flat uniform medium, but in a medium that goes as R to the minus 2. So it doesn't look like much on this plot, but it completely changes the profiles inside of the shocked region. Particularly, the density is peaking as a contact discontinuity instead of going down. So what happens when you use this kind of models? So these are computed, these are initial models that I didn't say that when I explained how we do that. So I start at a young age with this profile that includes the shocks, because when you use such power laws for the ejector and the ambient medium, you have analytical solutions for the young supernova phase from Chevalier. And then I do the hydro simulation at later phases with Ramses. And so the top one is what you've seen before, like a thermonuclear one like Tycho. The bottom one is a core collapse one like Casey. And you see differences in the way the relay fingers are growing. But otherwise, the differences in terms of particle acceleration were not so important. And actually, so it's the same kind of effect that you will get, that it depends on the energy at which you observe on the magnetic field evolution assumed. And it's actually less visible in what I did so far in the core collapse case, because it's more dominated by the ejector, and here I'm only doing particle acceleration at the forward shock. But it's, and so very quickly, another interesting one for circumstellar, the circumstellar medium is SN 87A, so a super recent one, but not in the galaxy. Is it in the LMC or in the SMC? Yes, the LMC here. And so it's been growing for a few decades now, and this is an example of simulations going from the supernova to the supernova remnant done by Orlando's group. And so these are observations with Chandra. What you see is a ring of material that's around the explosion site, and that's probably caused by the progenitor. And so in the few past years, we've seen it being brightened up by the blast wave. And so they are able to reproduce this and make predictions of what's going to happen next. But they were doing this from a 1D supernova model, and we...
In the synthetic observations, what is it that gives rise to the discrete bright spots? Is there some breaking of the symmetry of the ring that leads to that?
Yeah, also I don't remember the details for this one, but it must be imposed somehow in the initial conditions because what they use for the supernova is purely 1D. And I don't know, it seems too big to be the related stuff that I should like. I would need to double check. So, I mean, we can do after, but so just wanted to show this one briefly because they have teamed with our lab, the ABBL at Riken. They want to redo something like this, but using a more realistic supernova model. And so my colleague Ono-san, he did simulations of nucleosynthesis for a core collapse supernova remnant, and is in 1D, 2D, and currently is doing this in 3D. And we got a European press project accepted to do the simulations of this. That was just to mention this, was bringing me to this main topic of going from the supernova to the remnant, because really, so I've been showing simulations of supernova remnants, but people who do supernova remnants and people who do supernovae, these are actually different communities, like different physics, different problems. And I think it's now necessary to make the link between the two. And so I'm just briefly going to review what people are doing in the field. Oh, a bit more. Really briefly going to review what people are doing on the supernova side, and we want to use this. So it's not going to be complete, it's probably biased from the collaborations we are setting, but to give you an idea of where we're going. So there's the two cases for the core collapse. It's still not clear how you get actually an explosion. So the idea is that when iron is burnt, and you can no longer burn the material, and so it's going to collapse. And the hope was that it would trigger the explosion, but really, usually as it collapses, you get some accretion shock that actually stalls and not an explosion. So you need a way to revive the accretion shock so that it gets out and disrupts the star. And you can check the reviews by Janka if you want to know about the latest developments. But so a key ingredient is asymmetries caused by instabilities and turbulence, and to get the energy input to actually get an explosion. Most people, not all people, but most people believe that it's coming from neutrinos. Okay, so for core collapse, we know that there is a huge release of neutrinos. And so people are thinking that the explosion is actually driven by neutrinos. And so these are fairly complicated simulations where they do maybe magnetohydrodynamics, including neutrino physics with some nuclear equation of state to get from some progenitor models. So again, this is a different community who does the star evolution and gives them models. And with all of this, with or without gravity and GR taken into account, they try to simulate the explosion and then get the observables, typically light curves and spectra of the yields of the different elements. And so speaking about dimensions, so we want to do the 3D simulations. So this is really done by stages, and actually the stellar models are 1D. And here, first they were doing 1D models, and they were exploding sometimes. And then they were doing 2D models, and it seems to be better, like more explosions. But 2D, I'm not sure what a 2D supernova is. So really you should go 3D, and now they're doing 3D models, and it's not looking better, actually. It's not so good for the explosion. So there's still not a consistent path to get successful explosions. But there are models that explode and some that don't. And so again, you can ask these people, this one is quite confident that they're on the right track, but it's still not clear why and when it explodes. And even this layer, this is actually multiple steps. And people will do first the collapse itself, which is less than a second. And then they will do a subsequent simulation of the propagation of the shock from the explosion inside the star that burns the rest of the star and disrupts it until it gets out of the star envelope, what they call the breakout. And so these are just some examples of Anop Watanarat is one of my colleagues. It was at MPA before that, the Max Planck group. It wasn't MPA before, it's at Riken now, and is going back to MP. And the longest simulations they've done so far, published so far. So this is it going from second scale, that's really the explosion itself, to hour scales when it's really getting exploding the star itself. And these are different models from different progenitor stars. And so I won't get into details, but you see how different stellar structures give you different geometries of the ejecta initially. And the question is it going to stay? Do we see that in the remnant? And if they pick this model and look at the iron and the titanium, they can by pure chance, reproduce something that looks kind of like what is seen in CITA. So like this is a 3 image, and you get 3 blobs in red of iron. And the color is different here. So this one, you'll have to check the green one. And so they get these like big blobs of iron by chance in this particular model, which is looking like what you see in CITA. So this is by no means a proof that this model explains CITA, but it shows that in principle you can, this could be at hundreds of years still the impact of what happened at the explosion itself. Except that this is just hydro, and so they still need to compute all what I said before, the ionization, the thermal emission, and so on. And so this is where we plan to collaborate, so to get from this to actual observations. And that's another work that was done on CITA by Orlando again. So Orlando's group did work on this. And what they did here, they actually simulated the supernova remnant evolution and the emission, but they started from a 1D model where they put asymmetries by hand. So like they added some clumpiness, they added some pistons until they could reproduce something that looks like CITA. So it shows that, again, the asymmetries can be from the explosion itself. But so now we want to get something that covers it all. Okay, so can I get a few more minutes so that I can actually show the main thing that I am currently doing, which is on thermonuclear supernovae, so explosion of a white dwarf. We don't know still if it's like a single white dwarf that's accreting or 2 white dwarfs that are merging, or maybe other scenarios. And we are collaborating now with Fritz Röpke, who's been doing simulations of thermonuclear supernovae. So like these are examples of simulations in 3D. And so the question is, this is what I did, and this fluffiness is purely caused by the evolution of the blast wave, okay, starting from purely uniform initial conditions. So the question is, when we start with this, what do we get after? And so I'll go fast this, but so how do you do a thermonuclear explosion? You have to ignite like the thing, and so that has to be parameterized. So they did a grid of 16 models, 16 different ways to start the burning at the center of the star. And we are going to use one here, which gives the yields of nickel that are the most promising. And then there's the explosion itself, there's a flame propagating inside. And the question is it propagating subsonically, then it's a deflagration, or supersonically, it's a detonation. And one of the most popular models is actually a transition from deflagration to detonation, what they call the delayed detonation, or DDT. And so that's maybe the most standard model, and that's what I'm using. But this is just hydro. But after this, they compute nucleosynthesis in post-processing with, I don't know, like hundreds of isotopes that they get the distribution in 3D. And so this is what I want to use as input for my simulations. So before I was using this, no, I skip this. Okay, so this is what I'm going to use. This is the distribution of nickel 56, which is going to be iron, oxygen in green, and carbon in blue. Maybe I should. No, I don't. Quickly. Oop. These are two isocontours in the density. This is a 3D. And so you see it's kind of spherical, but not really symmetric. And these are just 3 elements. So again, that's nickel in red. That's going to be iron, which is in the center, oxygen in blue and in green, and carbon in blue. So you see how it's distributed, and this is what I'm using now, what I'm going to use as initial conditions for my own simulations. Come on. Where are you? Yeah. And so that's a custom-made thing that I did. If you come to our lab, I will be able to show you in actual 3D how it looks like using VR headsets like this. So it's something I started last year with people at the U of M, and then my boss visited the U of M and he liked it, and so now we have one on campus. And so now that's the final slide. So just what I get when I'm using this as an initial condition instead of this, which is the Chevalier profile with like azimutally symmetric initial conditions. This is the supernova input averaged, so just a different radial profile, and this is the full 3D thing. And if I play this, so that's what you've seen before, and that's from a realistic supernova model. And what is interesting to me is all the Rayleigh Taylor of the blast wave phase is growing on top of the existing instabilities from the explosion itself. And in particular, the fact that the blast wave is distorted, which is something that I never had before. Like you would have these fingers growing and getting close to the blast wave maybe, but not something like that. And if you remember Tycho's image, you actually see like part of the ejector that seems to be ahead of the blast wave. And so it's interesting. But in any case, it is showing that even at 500 years, if you start from this, you still see the impact of this different initial profile. So it looks like we actually can see the effect of the explosion itself even after a few hundred years when we look at the supernova remnant. So that's just like the very first results on that, but that's what I'm working now. There's still a lot of things to do, like for the space resolution and start at an earlier age and see how it goes. And then I can compute the ionization, the thermal emission, and actually compare to observations. So still quite a lot of work, but I think it's really interesting to do this now, because so even for thermonuclear remnants, which looks simpler maybe than a core collapse one, this shows that you can get the imprint of the explosion in the remnant. And I'll stop here because it's been too long.
Do you have a way to tell if you see some feature in the remnant, whether it's reflecting the ejecta distribution or the circumstellar medium?
Yeah, that's a good question. I don't know if I have an easy way to tell them apart, because so this kind of effect, you can also get that from the clumpiness of the ambient medium. Like Orlando again did things like that. And so it's not obvious a priori how to disentangle the two. So what we have to do first is to simulate them separately and see what they produce. And then maybe I will be able to give you a more more useful answer and to tell you what can come from what exactly. But so this is the kind of thing that we have to explore. Yeah.